In my experience, libraries that use proxy types, they usually don't advertise it, but they often will document it. It's important to understand that this is an implementation technique. It is not part of the conceptual API. But library implementers understand that, especially with the advent of auto, you're going to need to know when proxy objects exist and when they do not exist. So by checking the documentation, that will often give you a hint to that. If you suspect that there is a proxy type being used, either because you're getting strange behavior in your program, whatever it happens to be, you can check by examining the header files. This is not the easiest thing to do. But if a function conceptually returns some type, but it actually returns some other type, then T2 would be a proxy for T1. So as an example, from the header file for vector, if here's vector of bool, now the function call, the array bracket operator for vector of bool returns a reference. This is normal. That's every vector returns a reference as part of its array bracket operator. So the fact that this returns a reference, that's not a surprise. What is the surprise is that reference is not an actual reference, it's a class. So if you are familiar with the fact that normally a vector returns an actual L value reference, and now it's returning a class object, that is what can tip you off, this is actually using a proxy type. If you have discovered that you're using a library that uses proxies, and you still want to use auto, which is reasonable. Auto still has a bunch of advantages. What you can do is you can tell auto what type to deduce, in particular by casting the proxy expression to the appropriate type. So what I can do is I can say, I still want to use auto, because number one, I want to fall into the habit of using auto. I want to make sure that I initialize it, that I can't forget to initialize it. But in this case, auto will deduce the wrong type. So I can call make bool vec of 3, and then I can cast it to a bool. I'm basically saying, this is the type I want you to deduce. And that's what auto will deduce. Herb Setter has written about this. He calls it almost always auto. This particular idea of take an expression which has one type and then cast it into a different type so that auto will deduce the right thing, I believe deserves its own name. I call it the explicitly typed initializer idiom. As far as I know, I'm the only person who calls it that. But perhaps the name will catch on. But the idea is to use an expression which doesn't have the type that you want, and then tell the compiler what type you do want.
Why wouldn't you just initialize bit to bool?
So the question, essentially the question is, why use auto and why not just use the bool instead?
Yes,
there's a couple of different reasons. One of them is, if you want to fall into the habit of using auto, you just get used to using it all the time. So it would be for consistency with your other declarations. Another one would be mandatory initialization, which is so you can't forget to initialize it. Now, there's another example I have too. It's a little different presentation, so give me a minute and we'll find it. Because it actually, in some cases, I think, can lead to clearer code. This is from a slightly longer version of the same presentation. Let us suppose that I have this function calc epsilon that returns a double. And let us suppose that we know that for our particular application, we only need float precision, and the difference in size between doubles and floats is something that we care about. So I can call calc epsilon. This is going to return a double. I can use the explicitly typed initializer idiom to cast it to a float and put the result in an auto. Now, that does not answer your question, because your question was why use auto? So, notice that if I actually do the cast, it takes more words here. It takes more words here too. So I can't even argue that it's short. However, it's consistent with this general advice about preferring auto. You can't forget the initializer. But especially in this 32 here, with this code here, if I say calc epsilon, and I put the result in a float, it is not obvious to the reader of the code that I have deliberately made a decision to ignore the double precision this returns and to store it in a float. On the other hand, if I call calc epsilon and I cast it to a float, this says very clearly, whatever this thing returns is not a float, and I'm deliberately choosing float for some reason. So I think that this is actually more expressive about what we're trying to say, which is, I know it returns a double, but a float suffices for me here. This code does the same thing, it just doesn't say it as clearly in
I agree, but still, in the first example, you know, because you cast, you know explicitly that the type is float there, EP, nothing else. Well,
this code here suggests that this does not return float.
yes.
Otherwise, I wouldn't need the cast.
Yes.
So the
But
advantage
EP is a float. So in both cases.
No, these do the same thing. These both do exactly the same thing. The difference is that in this case, we are getting an implicit conversion from a double to a float, and in this case, we are getting an explicit conversion from a double to a float.
Okay, May, another question. The benefit of always preferring auto, how does it work with all the magic tools that would analyze the code, both like when you write an IDE or static analyzers?
Okay, so the question is there some kind of interaction between auto and, for example, static analysis tools or IDEs or something like that? The first thing to recognize is that auto is a completely statically determined type, which means that if this is what you type, it is exactly the same as if you put the word float here. And any decent static analysis tool will see that, which means that static analysis tools will see exactly the same types as are actually there. So that should not be a problem for those. And as far as IDEs go, these days most IDEs actually are parsing the program as you're typing it in, which means you can usually hover your cursor over a variable name and it will tell you the type of the variable name, and that works with auto exactly as you would expect.
But there's something like forward, it might not.
I'm sorry?
But there's something like forward, with forward where you have to decide.
Remember that forward is a cast that's done entirely during compilation, not a runtime decision. I can think of no reason why using auto in your program should be a problem for tools, because it is still completely statically determined. There's no runtime decision making. Okay? Yeah.
What if a library changes its implementation during time? How can they protect against simple bool reference and class? Okay.
All right. So the question is, let's suppose that the library changes its implementation. How can I protect myself? There's actually two schools of thought on this, interestingly enough. If you use auto, then if an interface changes in some way, if I have a function and its return type, for example, changes, then if I use auto to store the result of its return type, I automatically update to get the appropriate new return type, which means I'm more resilient in the case where the library interface changes. The other way to think about it is to say, well, okay, but let's suppose they replace a real type with a proxy type. And I was using auto, now I might end up with these kinds of situations. I think that's relatively uncommon, but having said that, interface changes in general can break arbitrary amounts of code. That's the whole point about interface. So I don't think there is no way to completely insulate yourself from changes to interfaces, which is why interfaces don't get changed very often. Usually libraries keep their interfaces and change their implementations. All right, that's the best I can say for now. Okay. As far as code clarity goes, we could have a long discussion about that. I will simply say that Auto is a tool. It is not an obligation. If, in your professional opinion, you believe that your code will be clearer by writing out explicit types, great, write out explicit types. There is nothing about C++ that says you must use Auto. It is a tool that is available to you. But I do think it's worth noting two things. The first one is, I've already mentioned that IDEs can show the types of auto-declared variables, in many cases by hovering over a parameter type or an object name. So usually they're not completely invisible. The other thing I want to point out is C++ is not blazing new ground here. There have been languages for decades that have used static analysis and type deduction in order to figure out what types are, and people have written large-scale production quality shipping products with them. So C++ is not trying a brand new experiment as far as programming language is concerned. C++ is adopting ideas that have been used in other programming languages for a long time with great success. So again, if you honestly believe that your code will be clearer by not using Auto, fine. Use your best software engineering judgment. But at the same time, bear in mind that the technical advantages I showed earlier do exist, and C++ is simply catching up to other languages in terms of deploying this technology. So the guidelines are to prefer Auto to explicit types for declaring objects, and to remember that Auto plus initializers yields an initializer list. That is completely true in C++ 11 and in C++ 14. And compilers may start changing because they adopted N3922, but especially if you're writing cross-platform code, individual compilers are the one thing that does not change what the standard says right now. Any questions about using Auto to declare objects? I now want to talk about universal references from R-value references. This is the crux of the matter. If you have an R-value reference in the source code, it's going to look like TypeRef. And it would be natural to assume that if I see TypeRef in the source code, that means I've got an R-value reference. That's not true. That's the problem. TypeRef has two different meanings. By the way, I'm lying too. But the reason I'm lying is because it's really useful. For many purposes, the truth, which is reference collapsing, simply confuses the matter. But we're going to cover the truth later, so by the end of the day, you can decide whether you think that the idea of universal references is a useful idea or not. What I will say is that even the people on the standardization committee have finally come around to recognizing that it's a useful idea. We'll talk about that a little bit later. Right now, we need to talk about the double meaning of TypeRef. If I say I've got a function which takes a parameter type widgetRefRef, this is an R-value reference, just like you would expect. If I say widgetRefRef variable 1, this is an R-value reference, just like you would expect. If I say AutoRefRef, this is not an R-value reference. If I say template, void f takes a vector of trefref, this is an R-value reference. If I say template type name t takes a trefref, this is not an R-value reference. Now, it is not obvious by looking at these examples what distinguishes an R-value reference from a non-R-value reference. So that's what we need to do now. Yeah.
But if, for example, I would write similar to the third line, I would write declaration type, parentheses, var 1, var 2 equals var 1. So then var 2 would be
What do you
so the third type var1.
Just like that?
Yes.
Like that?
Yes. What would keep it?
Okay. For purposes of this discussion here, I will point out that this line here doesn't have any refs. So it's actually independent of this discussion because what I'm trying to get across here is the meanings of this particular symbol. All right? Having said that, since we're already in the neighborhood, okay, var1 is an R-value reference to a widget. So the decal type of var1 will be an R-value reference to a widget, which means var3 will be an R-value reference to a widget. And I'm trying to initialize it with an L value, var1, and the code will not compile. Because I am attempting to initialize an R-value reference variable with an L value. And you cannot bind L values to R-value reference variables.
The same would be if instead of decal type var1, I would write widget refref var3. It would compile it.
Okay, so now I think what we want to do is get rid of that type and do widgets
Yes.
for equal var1 like that.
Yes.
Okay. This expands into this. So var4 is an R-value reference. R-value references can only bind to R values. That's an L value. It has a name. So this won't compile either. These two lines will not compile for the same reason. And again, for purposes of this discussion, they're not relevant because the only thing we care about here is how do you tell the difference between this, which is an R-value reference, and this, which is not an R-value reference. Okay? Yeah.
About the decal type, does the rule that a reference is removed for names is works only for L value references?
The rule for decal, the question is about removing references from names. You only take decal type if you give it a name, will give you the exact declared type of the name. The only place we saw where the reference was removed was on template type detection. Decal type, if you give it a name, it will tell you exactly what the type of the name is. In this particular case, variable 1 is a widget refref. So decal type of variable 1 will be widget refref. Does that answer your question?
Yes.
Okay. And just for completeness sake, if you pass variable 1 to a template, the type deduced would be widget, because it throws away the references. So the decal type behaves differently from template type deduction. Yeah.
So I can question back to the first example with the function.
Yes.
Wasn't that before we discussed that in this case we don't know if it's R-value reference or not?
All right. So the question was, didn't we say earlier we don't know if it's an R-value reference or not? In this particular case here, it is an R-value reference.
Okay.
Now, I haven't explained yet how you tell the difference between an R-value reference and a universal reference. So let's go a little bit further and you'll be able to tell the difference. This is the thing. When you see a type and then refref, the refref either means an R-value reference. If it means R-value reference, if that's what it means, it only binds R values and it facilitates moves. The purpose of an R-value reference is to identify objects that can be moved from. That is the purpose of an R-value reference. It is to identify objects that can be moved from. But if you see TypeRef, it might not be an R-value reference. It might be a universal reference. A universal reference is an R-value reference, or it is an L-value reference. It is syntactically TypeRef, but it might actually, in practice, prove to be a a TypeRef. It can go either way. It binds L values and it binds R values. It can take const and non-const. It binds everything. It's universal. Anything that can be bound to a reference can be bound to a universal reference. It might facilitate copies. It might facilitate moves. Now, this term, universal reference, is new terminology. It is terminology I invented about 2.5 years ago because I thought it was important to be able to talk about this thing. And about 2 months ago, some people on the standardization committee came to me and they said, Scott, after 2 years, we finally agreed we need to have a name for this thing. We like the fact that it means something different from R-value reference. The only thing we don't like is the name you came up with. And so they said, we want to call it a forwarding reference. So, newer terminology. And in fact, there was recently a document adopted last week by the Standardization Committee introducing the word forwarding reference into the standard. Currently, you are going to find more references, for example, on the web to universal reference because I've been talking about it for a couple of years. It is my expectation that eventually forwarding reference will become the accepted term for it. I don't frankly care what they're called, as long as we agree on what they are and how to use them. So, practically speaking, universal reference, forwarding reference, they're the same thing. In my talks, I'm going to be using universal reference because it's the more common term right now. You're all smart people. I'm still going to point out LRef means L-value reference, RRef means R-value reference, URef means universal reference. Not too complicated. Now, universal references arise in two contexts. There's two places to look for them. The first one is function template parameters. And the second one is auto declarations. By far the most common is templates. By far the most common is templates. So this is the gist of the situation. If you have a variable or a parameter whose declared type is TrefRef for some deduced type T, it's a universal reference. Notice that there are two criteria. First, the form is TrefRef. The form is TrefRef. Any other form and it's not a universal reference. And there has to be type deduction. If there's no type deduction, there's no universal reference. So, if you see TrefRef and you have type deduction, you have a universal reference. Otherwise, it's just an R-value reference. I'm still lying to you. We'll get to the truth eventually. A universal reference is a reference. Every reference must be initialized. The initializer for a reference, the initializer for a universal reference, determines whether it is an L-value reference or an R-value reference. If you have a universal reference and you initialize it with an L-value, it becomes an L-value reference. If you have a universal reference and you initialize it with an R-value, it becomes an R-value reference. You can think of a universal reference as something sort of like the chrysalis of a butterfly. The chrysalis of a butterfly, eventually it's going to become something, but it hasn't become that yet. A universal reference will become an L-value reference or an R-value reference, but until you see how it's initialized, you can't know which one. I have a template that takes TrefRef as a parameter. Now, this is a function template. That means we have type deduction. It has the appropriate syntactic form, TypeRef. These two things mean it is a universal reference. W is a widget. If I call f of w, this is an L value. I am initializing this parameter with an L value. As a result, TRefRef becomes just widget ref. And an L value argument causes an L value reference to be instantiated here. If I call the same template with the same object, but I cast it to an R value, remember that move just casts to an R value. If I call f with an R value widget, then this becomes an R value reference, and the function that's instantiated is f of widget ref. This is important. This calls a different function from this. This calls the function f of widget ref. This calls the function f of widget ref. They're completely different functions. They have different function signatures. This, by the way, is why universal references are convenient. It allows you to write a small amount of source code and generates a large number of template instantiations. Now, if you don't want too many template instantiations, that's code bloat and that's a problem. But if you need those different template instantiations, then this is a very efficient mechanism for writing source code to generate the instantiations that you need. If I call f of widget open close, this expression, widget open close, creates an unnamed temporary widget object. No name, you can't take its address, can't bind a reference to it. The result of this temporary is an R value. As a result, it instantiates this template with widget ref. These two calls call the same function. That calls a different function. Yeah?
I have a question. If I specify the template parameter explicitly, then there will be no time reduction. So there will be simple error reference, no universal reference.
Okay, so the observation is, if I were to call the function f and actually pass in the type t, then there's no type deduction any longer, in which case universal references don't apply. It turns out that in order to figure out what actually happens under those conditions, then you have to fall back on what's known as the reference collapsing rules, which we will cover after lunch. But you are completely right that if you explicitly specify the template parameter, then you no longer have type deduction, and as a result, thinking about things as a universal reference is not going to be helpful. I say AutoRefRef val is 10. Now, this is the proper syntactic form. TypeRefRef. Type happens to be auto. And because it's auto, we get type deduction. So the two necessary elements are present here. AutoRefRef is a universal reference. I'm initializing it with an R value of type int. Because it is an R value, this becomes an R value reference, and val's type is int ref. If I have a vector of int, and I say v sub 5, v sub 5 returns an int ref. That's just what the array bracket operator in vector returns. And L value references, by definition, are L values. Just as a language rule, by definition, every L value reference is an L value. Which means I am initializing element with an L value. AutoRefRef is a universal reference being initialized with an L value, and as a result, the type of element is int ref. Somebody asked earlier about AutoRefRef. AutoRefRef, as I already mentioned, is uncommon in user code. It actually happens to be the underlying basis for range-based fors. So if you read the standardization document, which I do not recommend, if you decide to read the standardization document, please put on protective clothing first. It is hazardous. But a range-based for loop is defined, this is part of the definition, but notice the AutoRefRef. Again, it's in user code, the most likely situation for using AutoRefRef is going to be in C++ 14 lambdas, which contain AutoRefRef parameters. If you don't have type deduction, you can't have a universal reference. This function takes a widget ref. Notice that the widget type is specified. There's no type deduction going on here. It's a widget. This is an R-value reference. Here's a template, tref. It has the proper syntactic form. The type T will be deduced. This is a universal reference. I have a templatized class gadget1, and it takes as its constructor argument a gadget1 ref. Now, there's no type deduction going on here. If I'm in the class gadget1 of int, this type is gadget1 of int. If I'm in the type gadget1 of widget, this is gadget1 of widget. There's no type deduction going on here. Yes, there's a template. Yes, there's a ref, but this is not a deduced type. As a result, this is an R-value reference. Here's class gadget2. It has a constructor. This constructor is itself a template. The form is type ref. T2 happens to be the name of the type ref. We have type deduction. We have the proper syntactic form. This is a universal reference. So we're beginning to learn what to look for to identify universal references. Where things get tricky is that not all occurrences of tref in a template are universal references. Let me pause for a moment and tell you why I'm explaining this. It is because if you cannot distinguish universal references from R-value references in source code, you will not be able to read the source code and understand what it is doing. This is especially the case if you ever look at standard header files. So if you ever have to look at a header file for vector, or for any of the STL algorithms, for example, or for list, or name your own standard type, you are going to find universal references mixed with R-value references in many, many places. And if you do not know which one is which, you will misread the code. That's why this is worth learning about. Speaking of vector, here's a class vector. It's templatized on T. I have a function pushback. It takes a tref. I'm in a template. It's a tref. At first glance, it looks like it's a universal reference, but it's not. Because there's no type deduction present here. Think about how the class would be used. If I say I have a vector of int vi, when I call vi sub pushback, now, the member function pushback can't exist without a class, because it's a member function. But if you know what the class type is, if it's vector of int, t is int. If it's vector of widget, t is widget. And the way this code is going to be used in practice is someone's going to say, I've got a vector of int, and then they're going to call pushback. But this pushback is pushback in vector of int. And in vector of int, t is int. This is an R value reference. There's no type deduction going on here. The type t was never deduced because this is a class template. The type t was passed in. Remember, function templates can deduce types. Class templates can't. This pushback, the t here is whatever t was specified for vector. So if I call pushback of 10.5, because I have a vector of int, pushback actually takes an int ref. It takes an R value reference to an int. So the type of argument that's passed is double, but the parameter type is actually an R value reference to an int. Any questions on why this is not a universal reference?
It is clear, but perhaps it would be helpful for the previous slide to also have the gadget 2 constructor that takes T1, just T1 ref, and explicitly say that it is also an just a plain R. Yeah.
So the suggestion is that maybe this example should be augmented to have a constructor taking just a T1 ref.
So that would remain,
exactly.
And one more. Yeah.
Exactly, but that's a good idea. I like that idea.
Yeah.
Okay. Other questions about why this is just an R value reference? Yes?
Whenever I pass like some integer literal to this function, and then I print the address of it, what is the address? Where is it taken?
Okay, so I think your question is, well, the question is, if I take the address of this parameter, then the question is, what am I taking the address of? The answer is, and it's the same answer for all parameters. You are taking the, in this case, this is a reference. All right, so what's going to happen here? In this case here, I'm passing a double.
Yeah.
The parameter type is int ref. So, here's some memory, and it has the value 10.5 in it. So then what I do is I pass that 10.5 up to pushback. Now, here's the reference x. It has to refer to an int. So what happens is this 10.5 is truncated to become 10. Do this a little different. We know that x is a reference, which means it has to refer to some chunk of memory. And it's a reference to an int. So it's going to refer to some memory that is of type int. When the compiler sees that it's passing a double here, the compiler takes the double, truncates it to get 10. It then takes the 10 and it puts it into a temporary location on the stack. And it makes x refer to it. Does that make sense so far?
So it copies the value.
Pardon me? Okay, your comment was, it doesn't actually copy the value, because notice that this is a double, and this is an int. So it actually creates an object of a different type, and it then truncates the value. So it isn't, I wouldn't call it a copy. I would say it creates a temporary integer initialized with the double. The amount of memory needed for the int will presumably be less than the amount of memory needed for the double. I'm going to refer to this memory. Now your original question was, if I take the address of x, what am I taking the address of? And the answer is you're taking the address of this temporary chunk of memory that the compiler put on the stack for you.
Yeah, but if it's some big structure, it creates a problem with it? Or,
Well, the memory is just allocated to any function calls.
If I change this example, okay, I now have a vector of BHO. BHO stands for Big Honkin' Object. It's a big object. Uses lots of memory. It's a big honkin' object. So in this case here, so pushback will now take a reference to a big honkin' object. I'm passing it a double. Let us assume there is a constructor for a big honkin' object that takes a double. Then what will happen is we will create a big honkin' object, so I'll adjust my picture now. So when this code is executed at runtime, we will create a big honkin' object in memory. It will be initialized from the constructor with 10.5. So this will be constructed from 10.5. X will now refer to it, so it actually has a name, X. At the end of pushback, this big honkin' object will be destroyed. Does that answer your question?
what is if I pass a big array of integers?
The only time you're going to get a temporary created is if the type here is not the same as the type here.
Oh, okay.
It's only because the types are different. Now, if I passed a big honkin' object here, this would just bind a reference to it. So you normally won't get a copy.
Okay.
You only get a copy if there's a type mismatch. Does that clarify?
Yeah.
Okay?
But the pushback anyway copies the information to the object in the vector later.
Okay, so the combination of pushback copies its argument into the vector. To be slightly more precise, this particular pushback, because it's taking an R value reference, will do a move into the contents of the vector. So X will, in this case, will be moved into the memory for the vector, not copied.
But it will be still destroyed at the pushback. As it is a temporary object constructor, then it is moved to the...
If a temporary object was created, again, you only get a temporary if there's a type mismatch between these two. Okay? Let me, just to be a little bit clearer here. Okay, so in this case here, I have a big honkin' object. And then what I do is I do a move of the big honkin' object. That just turns it into an R value. That binds the reference here. So far, no object has been created. There's no temporaries at this point. Inside pushback, it will then move the big honkin' object into the vector. And this reference will then be unbound. And at the end of this statement here, this object, big O obj, this object continues to exist. It has not been destroyed. However, it has been moved from. So, pushback does not inherently destroy anything. It depends on what's passed to it. On the other hand, if we have a call that looks like this, which is more typical for this particular in this case here, I'm creating an unnamed temporary big honking object. That's an R value. The constructor will be called here. It'll be bound to the reference X. Nothing will be created. It'll then be moved into the vector. At the end of the call, this local object, this temporary, will be destroyed here. But for purposes of our discussion, remember, what we're trying to do is to figure out how do I tell whether it's an R value reference or a universal reference, because that determines what the code is doing. And as we'll see shortly, it also determines, do I use move or do I use forward on it? For our purposes of discussion, all we really care about is this is not a universal reference, even though it's TypeRef. Because the type T is not deduced, it will be dictated by the person who actually created the vector. Let's take a break for an hour for lunch. And you go down the ramp and then around the corner, and the restaurant is as far as